Please let me know when you can see my screen, Rob.
I can see your screen. Looks like it's ready to
Okay.
go.
Okay, perfect. Sounds good. Okay, without any further delay, let's get into the presentation. I'm going to talk about a topic which is not very discussed in oil and gas quite often, just because it's a little bit intricate topic. So I will try to dissect it and try to divide it into topics which are a little bit more digestible. So we are going to talk about downhole completions. Whenever we talk about, or whenever you will hear the term completions in oil and gas industry, a lot of times they are referring to the hydraulic fracturing. They are talking about production. But we are going to talk about downhole completions. We are going to talk about the hardware that is used for the downhole completions. And we are going to see how that selection of hardware can affect your performance and your production. So the overall agenda and objective would be to talk about downhole completion concepts, basic element of completions like tubing and work string. We are going to talk about packer because that is a term that you will hear quite often. We're going to talk about perforation, downhole, artificial lift, and downhole tools. So let's talk about why the completion is important and what is the role that downhole completions play in a production of oil and gas well. So if we talk about downhole completion, the definition is that the methodology and technology that is required to produce hydrocarbons. That means selection of tubing, selection of components, selection of hardware to produce all that oil and gas that is stored in a reservoir. The process involves designing, selecting, and installation of tubulars, tools, and equipment that is located in the wellbore for purpose of production and injection of liquid. So sometimes you are producing oil and gas, sometimes you are injecting different type of fluids. For example, sometimes we are injecting all that produced water from all the other wells into another well. Sometimes we are injecting nitrogen, sometimes we are injecting carbon dioxide, which is a very common theme right now, carbon capture and sequestration. In carbon capture, we capture all that carbon in the air and then we convert it into a liquid and then we try to store it in a reservoir. So the definition, and so this not only includes selecting and installing, but as well as logging, perforating, and testing are also part of the completion process. In addition, complex wellheads that are installed at the top of the completion, processing and storage requirements also affect the production of the well. So selecting the right components, selecting the right hardware has a lot of bearing on successful production from oil and gas wells. We have talked about why we require an understanding of completion, but essentially there are three things that a completion system should provide. It should provide you a safe, efficient, and economic way of producing oil and gas. Safe in terms of well security and environment, efficient in terms of meeting your production objectives, and economic because whatever cost, because it is very costly, all that hardware or all the tubulars, they are quite costly. It should be economical in a way that the cost should be less than the revenue that is that oil and gas well is going to produce. So cost versus revenue needs to be balanced. A little bit on the completion technology evolution. The first open hole wells were drilled in a very shallow reservoir, which was sufficiently consolidated to prevent caving. As deeper wells were drilled, the problems associated with the surface water prompted the use of casing and conductor to isolate water and prevent slowing. So you can see that this is not a new technology. It has been around for quite some time. It has evolved for quite some time as well. Initially in 1800s, these were just simple holes that were drilled in the earth. But in early 1900s, we started cementing and started installing casing in these wells. In 1926, first ESP was installed, and that started the whole artificial lift revolution. In 1933, the first gun perforating job was completed, and 1969 coil tubing services were introduced. So the process has evolved quite a bit from where it started in 1800s. So what are the factors that affect the well performance? There are three big factors that affect the well performance. Number one is reservoir bond boundary. That means you can see over here in yellow, that is kind of your reservoir boundary. This can be estimated by different type of logging tools and different type of seismic surveys. Reservoir properties, that means the reservoir fluid, what type of fluid properties there are, the amount of H2S, carbon dioxide, the amount of water, oil, and gas in that reservoir that can be measured by different type of sampling tools, and then and testing technologies, and then completion. That means the tubulars that will go, if you see right over here, this is the item number 3. So the tubulars that go inside an oil and gas well to produce oil and gas, all that oil and gas fluid, that can be controlled. That means that is one thing which you can control: reservoir boundary and reservoir properties. These are the two things that can be measured and estimated, but they cannot be controlled. Completion is the only thing that you can control. And by controlling this completion design, you can actually effectively meet your production targets, or you can miss your production targets if you do not choose it wisely. So now you can very well understand that selecting the right completion design is very important when we are when we are producing from a well. These are some typical well bore geometries. The one which you see right over here on your left is one of the most typical, and something which is very personable, something which you can probably imagine as well, is the straight well bore profile. That means there is no deviation. The well goes straight from the top to the bottom. There is a cap rock, and then there is a basement. What is cap rock? You can see the cap rock is at the top and then at the bottom. Cap rock is a type of a rock that prevents the oil and gas from moving anywhere else. It is a less permeable or less porous rock that will act as a boundary to hold that oil and gas within certain space and certain volume. Basement is that volume that the cap rock is trying to contain. All the oil and gas effectively is in the basement. So your completion design is in a way that your perforations or your openings are right there in the basement, and there is no perforation and opening in the cap rock. And that is what you want. You want to estimate your reservoir boundaries so that you can deploy your completions where the basement is, and you don't want it to be open to the cap rock. Now, that was the most simplest well bore profile. There are other types of well bore profile. There is what we call the slanted well, which you can see right at the top. And then there is horizontal well, which you can see right at the bottom. In the shale evolution, or when we start talking about shale production, what you see is more of the horizontal wells. So it is drilled straight. It goes straight from the top, and then there is what we call a heel, and then it goes in a horizontal direction. Principal completion design factors. So completion design process has evolved as the complexity of the components and overall completion design has increased. However, principal factors shown as considered basic, and they have the most important role to play in almost all completion design process. So the factors are primarily your casing protection. So we're going to talk about casing, but casing is effectively the biggest piece of tubing in a well. You want to protect your casing from erosion and corrosion. Tubing string removal. You want to facilitate or ease, and you want to have the flexibility of removing your tubing string for the workover, or if you want to change components, you want to have that flexibility in your completion design. Safety and contingency. Safety in terms of deployment of safety valves, subsurface safety valves, or surface safety valves, and then your ability to kill the well if somehow it is coming to a point where your bottom hole pressure is increasing to to a factor where you cannot control it. So you want to have the flexibility of killing the well to protect the environment and protect any blowout or uncontrolled exposure of well fluid to the surface. And then production control. You want to have flexibility in selection of your components so that you can control your production. You can decrease your production, you can increase your production, and you can optimize the production from that well. That means nipples, profiles, and sliding sleeves in the completion design needs to be optimized for production of your well. Now, just consider it as if you have a glass of water and you have a straw, and imagine if you have a straw which is really, really small or really small diameter, and you are trying to suck all that water and you cannot do it optimally. You want to have a straw which is optimized for that glass of water. This is very similar concept as completion. You don't want to have very small diameter hardware because then it will constrain your production. It can actually hamper or it can actually damage the reservoir properties. So you want to have something which is optimized for that particular geometry. Some types of completions, there are primarily two types of completions. One which is right on over here, which is called open hole completions, and on the right hand side, which are called cased hole completions. So barefoot or bare or open hole completions, there is no downhole flow control or isolation. The production formation, which is right over here, is unsupported. The casing provides isolation between shallower formations. So this is your casing, which you can see right over here. It's a piece of tubular. The casing provides isolation between shallower formations. It's cemented production casing. There is no downhole flow control or isolation. While in case of cased hole completion, there is isolation between shallower formations, and you can see it's cased all the way to the bottom. So there is no unsupported formation. The formation all the way from the top, which is cap rock, all the way to the bottom, which is reservoir, is totally supported by the piece of tubular. And what happens is that another big difference between open hole and a cased hole completion is that in the open hole completion, you don't need any perforations, but in the cased hole completion, because your casing or your liner is running all the way to the bottom, you need perforations so that you can produce. Right? And this is also gravel pack completion is also type of open hole completion because there is unsupported formation, but then you have gravel pack at the very bottom. Gravel pack is essentially a piece of completion. It acts like a filter. So if there is a lot of sand in your reservoir, the gravel pack completion can actually help. It acts as a filter from sand, and it will prevent all the sand from going into the reservoir. Now a little bit more on the cased hole completion. This is what a simple casing completion looks like. You have a piece of tubular that goes all the way to the bottom, a piece of tube that goes all the way to the bottom, and you are producing from your reservoir. A liner completion is your casing will go at a certain depth, and then you put a small diameter liner at the very bottom to produce. And then this is what we call a single tube completion. Over there, you were producing through the casing. Now from here, you are producing through the tubing. That tubing is another small piece of tube inside the casing, and you are producing from here. Then this is what we call a tubing and packet completion. Very similar to the simple tubing completion. The only addition is what we call a packer over here. So packer essentially isolates the tubing from the casing from the wellbore fluid. So it acts like a seal. So your reservoir fluid will come and it will enter the tubing and it will go through the tubing. It will not interact with casing at all. Then you have tubing and packer with a tailpipe configuration. Tailpipe is essentially an extension over here, which lowers your tubing, and you can actually deploy your tubing a little deeper. And this is tubing packer with other components. So as you start increasing the types of hardware in your tubulars, for example, subsurface safety valves, sliding sleeves, then it becomes a tubing and packer with other elements type of completion. There are two types of producing zone. There are single zone completions and there are multi-zone completions. Single zone completions are used in reservoirs with less complex structures. So if you have one producing zone, you will use a single zone completion, which you can see right over here on your in the left-hand side of the picture. Selective perforating, one of the key to ensure successful completion. So you have essentially one pay zone or one reservoir, and you are producing from that reservoir only. But there are some scenarios where you have more than one reservoirs which are producing. For example, you have two reservoirs which are producing. In this case, in a picture which you can see on the right-hand side, you have two reservoirs, so you need two packers to isolate these two zones. So you produce from one zone that goes into the tubular, and then you have a packer. Go back, and then you have a packer right over here, and then you have another zone that is producing. So you are isolating two zones because two of the zonal properties can be different, and you don't want, for example, one of the zones can be low pressure zone, and the other one could be a high pressure zone. So you don't want what we call a fluid migration. So we isolate the two. This is what we call a multi-zone completion. So completion elements, let's talk about the tubing and the work string. Tubing and a work string. Tubing is essentially these big metal tubular components. Different type of metallurgies. The type of metallurgy depends upon your, obviously, your downhole temperature, pressure, and also your wellbore fluid. So as the conditions start becoming aggressive, that means high pressure, very corrosive liquid, you need a premium metallurgy. You need corrosion-resistant alloys, CRAs, to kind of, deal with that aggressive production condition. So these are the tubings. These are actually essentially produced by a mill, and then they are transported in bundles to a drill or a production site. So we briefly talked about the tubing string specification. The size is defined by the OD, the weight, and the wall thickness. The material grade, that means your pressure rating and your use strength, and then construction, which is seamless or electric welded pipe. So the tubing generally provides the primary conduit from producing interval to the wellhead production facilities. Therefore, proper selection, design, and installation of the tubing is very important for any completion system. The size and dimensions of the tubing must be sized to enable efficient production. The grade of the tubing should be selected to prevent failures from the tensile forces, internal and external pressures, and the corrosive nature of the wellbore fluid. The assembly of the tubulars, the components of the string must be installed to make sure that they are installed and they are selected, so they are not damaged when you are running them downhole, to provide a pressure tight seal. The tubing grades of the tubing are effectively judged and determined by API standards. API is American Petroleum Institutes. So there are API determines the grades and standards of the tubing. When the industry has to follow those standards and grades, ensure that there is a consistency across the globe. So a couple of factors when we are thinking about casing string design. You need to take into account your pressure and tension. That means the pressure and tension should be less than 80% of the tubing yield strength. That is the rule of thumb. They should also comply with the burst and collapse pressure ratings. It should be suitable for the production rate. Wellbore environment, that means it should be compatible with the wellbore fluid properties. That means corrosion and wellbore deposits. The connections of the tubing and the geometry should make sure that there is enough clearance, annular clearance. That means there is enough clearance between the tubing and the casing, and the tubing component should be selected so that they can endure the force and stress throughout the life of the completion. Here is just an example of, like, for example, if we talk about 278 tubing, you would know the weight of the tubing, that means the wall thickness of the tubing, the ID of the tubing, different type of grades, uh, the collapse resistance, the internal yield pressure. So if you would know what is the collapse resistance, that means the external pressure resistance and the yield pressure of that tubing, and then wall thickness and drift diameter. Drift diameter is the internal clearance of that tubing. So, what are the factors that can affect and damage your tubing? There are four principles that causes the length and force changes. These are piston effects, buckling effects, ballooning effects, and temperature effects. Um, Pressure buckling, which you can see right over here. What happens is that your tubing buckles if uh, there is high pressure in the tubing and low pressure on the outside of the tubing, and then if there are compressive forces. So if you are compressing your tubing and there is the high pressure is inside the tubing, then your tubing will buckle. Uh, Ballooning is when you have low pressure on the outside, high pressure on the inside, and you have you are also compressing the tubing. In that case, the tubing will buckle or will balloon. And reverse ballooning occurs when there is low pressure inside the tubing, high pressure on the outside of the tubing, and you are trying to stretch the tubing. In that case, reverse ballooning occurs and your tubing will kind of collapse. Piston effect, it effectively occurs when there is thermal cycling. So thermal cycling is that um, reservoir fluid properties sometimes will change. Your downhole properties will also change. So you will have these thermal cycles. What happens is that as the temperature decreases, the metal shrinks, and as the temperature increases, the metal will expand, and you will have these thermal piston effects, which can also damage your tubing. Let's talk about packer. We have talked about packer in last few slides, but let's see packer in a little bit more detail. So the packer is a subsurface tool that is used to provide seal between the tubing and the casing. You can see right over here a packer deployed. Packer is part of the tubing, and it provides the isolation between the tubing and the casing, um, thus preventing movement of the fluid past this sealing point. So before that, the fluid can interact with the casing, but after this point, after the packer is deployed, it cannot interact with the casing. So why do we need to run a packer? There are two factors that influence the running of the packer: production and intervention. From the production side, you want to run a packer to protect the casing, primarily protect the casing from the corrosive fluid, and to keep the high formation pressure of the casing and the wellhead. You also want to use packer as a means to separate production from different zones and also for the zonal isolation. From the intervention point of view, you want packer so that you can test your well, you can repair your well, you can do well stimulation, and you can also control sands. These are different type of packers. We are not going to go deep into the packers because it's an entire different topic. The packers, you can see they have, to provide sealing, they have elastomeric component, and to hold them in place, there are slips that hold the anchors in place. Let's talk about perforation. So what is perforation? So perforation is a process of creating a channel of communication between the wellbore and the reservoir. This should be achieved without damaging the inflow ability of surrounding formation to ensure that the perforations do not form a restriction on production capability of the completion system. There are generally different type of perforating options available for most completion applications. Selection of most appropriate technique will consider specification of completions, for example, the dimensions, the reservoir conditions, and local experience. So there, in the most common type of completions, what actually happens is that we will lower a perforating gun in the tubing, and that perforating gun, once it goes to the depth where your reservoir is located, it will fire these shaped charges and it will create these channels, which you can see right over here. These channels of communication will provide that communication between the reservoir and the tubing. And what happens is that after that, the reservoir fluid can actually easily flow inside the tubing. So I talked about the perforating in a very simplistic manner. What you can see is time by time evolution of that perforating process. At 0 second, you do not have, you will detonate the charge at 4 microseconds. What's going to happen is that charge would interact with the tubing. That charge and the high pressure, high temperature gases will create that small channel. And at 17 microseconds, your channel is created, right? So it's a very, it may seem a little bit complicated, but industry has been doing it for quite some time. It's a very controlled process in which we use explosive to create these channels. So fracturing and perforating, sometimes fracturing and hydraulic fracturing and perforating are used hand in hand in conjunction with each other. What actually happens is that you can see a cross-sectional view of a perforating gun. The perforating gun will fire and create all these channels. These channels will create all these fractures. And after these channels are created, we pump high pressure fluid in the downhole to open up these channels. And this high pressure fluid also have these propellants. These propellants will make sure that the channels will remain open even after perforating is done. So general production concept, we talked about production and we talked about casing and we talked about completion. Let's talk a little bit more about the general production concept. They're not very complicated. Let's try to dissect it. Let's see what you have in the picture. You have what we call your well bore fluids right over here, your production casing right or production tubing right over here, and this is your production at the surface. There are two pressures that you need to think about. There's a pressure which is called P naught. P naught is the pressure of the tubing, which you can see right over here. This is the pressure in the tubing. And PWF, which is the pressure in the well, which is right at the bottom. This is also called bottom hole pressure. This is also called reservoir pressure, interchangeable terminologies. And what actually happens is that there are two types of scenarios. If the P naught, which is the pressure in the well, is less than PWF, which is the pressure downhole, the well will flow naturally, right? Because if you remember Bernoulli's principle, the pressure migrates from high pressure to the low pressure, right? So your P naught is small, your PWF is higher, so your PWF will migrate towards the tubing, right? And you will produce naturally. Only 6% of the wells flow naturally. So a big number of wells do not flow naturally. Now, imagine a reverse scenario. Your P naught is higher than your PWF. That means that your pressure in the tubing, because of all that fluid column, is higher than your PWF. That means your bottom hole pressure. Now, the well will not flow naturally because there is a high pressure zone over here or high pressure over here. The PWF cannot migrate towards the high pressure, so you cannot make it flow naturally. Now, you need to think about other means where you can reduce your P naught so that your PWF becomes higher than your P naught. So you need to deploy artificial lift systems. What artificial lift systems do is that they decrease your P naught so that your PWF becomes higher, right? 94% of the wells worldwide would require artificial lift system, There are different types of artificial lift systems, your electrical submersible pumps, gas lift systems, progressive gravity pump systems, sucker rod pump systems, your jet pumps, your capillary lift, your plunger lift, all these are different types of artificial lift systems that are required so that you can reduce your P naught so that your PWF becomes higher than your P naught. This is what we call bottom hole flow. It's essentially a flow curve. You have your bottom hole flowing pressure, which is in PSI pressure, on your y-axis, and your flow rate, which is standard barrels per day, STV per day, of total liquid on your x-axis. And what actually it shows is that a flow curve between an artificial lift TPC. TPC is tubing performance curve. It shows a comparison between the artificial lift TPC and a natural flow TPC. What you actually see is that by decreasing the bottom hole pressure, which you can see right over here in the artificial lift system, by decreasing the bottom hole pressure, you improve your flow rate, right? So decreasing your flow rate, decreasing your bottom hole pressure, improving your flow rate, that is the purpose of artificial lift system. So although artificial lift systems may be installed later in the life of the well or reservoir, there is a clear benefit in preparing for artificial lift when planning the construction of the well. So proactively thinking about artificial lift when you are constructing the well goes a long way, and it actually helps to optimize your production. Relatively small modifications to the well configuration can provide flexibility and enhancements, which benefits the long-term production capacity of the well. For example, the following factors must be considered at the time of constructing the well and selecting the completion tubular. So you need to consider all these artificial lift methods when you are constructing the well. In US, for example, 84% of the wells are on artificial lift. 84% of them are on rod pumps. So your sucker rod pumps, 12% are on gas lift, and 2 to 3% uses ESPs and remaining methods of artificial lift, for example, hydraulic piston, jet lift, plunger lift, etc. So the worldwide division or spread of the lift system varies with the region and the type of the well. Gas lift, flowing wells, and ESP are more common in the new and high production fields, while a variety of other artificial lift systems are used in depleted and low production fields and wells. Wellhead configuration. Wellhead is the piece of completion which you see from your eyes whenever you visit or whenever you see oil and gas well. Whatever is downhole is downhole. You cannot see it, but wellhead configuration out on the surface is the one which you will see. So before designing a job, make sure you know the wellhead rating, you know the burst and collapse rating of the tubing. Usually you want all the pressures, yield pressures, temperatures to be 80% of the max pressure of the tubing wellhead and your production casing and tubing. So think of wellhead as this is a means of production. It is right there on the surface. Some people call it the parts in red, which you see right over here. Some people call it a Christmas tree. Some people call it a production tree. Depends upon the region, depends upon the area. It is called a production tree or a Christmas tree because it looks like a tree with branches. There are so the tree is essentially a combination of valves and spools, which you can see right over here in the picture as well. Different type of these hand-operated valves. They can be motorized as well. So these valves are essentially your lower master valves, your upper master valves, your wing valves right here on the wing, and then your upper swab valves. So by changing or opening or closing these valves, you effectively can change the production from the well. If you want to close down the well, you will close all these valves and your well will stop flowing, it will stop producing. And if you want to open the valves, you will make that well flow. And there are different series of pipelines that are connected to these valves, and then they will take the production fluid to the processing facility where you will separate oil, gas, water. The water will be either treated and injected back into the reservoir, or it will be disposed of. The gas will be transported to the pipeline network. The oil will go through tankers to a refinery where it will be refined for further transportation, and dividing that oil into diesel, different type of naphthas, different type of chemicals, and your typical gasoline. So with that, I think I've reached to the conclusion of my presentation. We have 20 minutes to go through the questions. So thank you very much for patiently listening to this presentation. Okay, I think we can take some questions. Let's start with Ismail. Ismail, if you have any questions. If you can unmute yourself. I think that needs to.
Yeah. Can you hear me now, sir?
I can, yes.
All right, good. Thank you, sir. Thank you for the presentation. Good morning, sir. Good morning, everyone. Yeah, this is my question. Since we are dealing much on the technologies that are related with the gas and the oil, so the question is this: how have advancements in technology, such as smart completions and automation, influenced the design and execution of downhole well completions? And what future technologies could further revolutionize this field?
Very good question, Ismail. So a lot of advancements in this field. You talked about the smart wells. The technology has evolved to a point where we have all these different type of valves in the well bore, or as a part of a completion, where they can actually open and close automatically to produce fluid, right? So what they do is that these smart valves will analyze the fluid coming from, if you have multi-zone completion, they will see how much water is coming from a particular zone. If the water increases, they will shut down that zone and they will start producing from another zone. Okay. So smart well is not a thing of future anymore. It is right there. And it is becoming more common around the globe, right? Smart wells right now are more common in the offshore production, but we have these electrical safety valves. We have these what we called electrical production valves, which are running if there is a cable that goes all the way from the surface to that valve, and all of it is actually happening with AI. So now you don't need to have a person sitting over there monitoring all these wells and looking at the production. The AI framework, the AI algorithms are actually trained that they actually control all that production in some of the fields around the globe automatically. So it has evolved quite a lot.
Thank you, sir. I'm grateful.
Okay. We can take another question. Suntam?
Yes,
if you can
Suntun, go
respond.
ahead.
We can't hear you, Suntam.
Suntum, we should be able to hear you. It looks like your microphone is activated. Suntum, can you speak? I think we can hear you.
Hello?
Yes, we can hear you.
Now it's possible?
Yeah, go ahead. We can hear.
Yeah, I said I would like only to thank Mr. Ali for his this class. It's a very wonderful. My worries or my question is to ask if we can use this kind of the gas technology in the sea or in the continental zones.
Sorry, can you repeat your question?
That's kind of the technologies, the gas technology or petrol, if we can use that in the rivers or in the continental zones.
Continental, sorry, what? I didn't get the last word of your question.
For my, what I want to say, Doran, do you make your explanation? I think that's kind of the machine is to use the exploration of gas or petroleum. Correct or not?
Sorry, Santam, I'm unable to understand your question. If you can type it in the chat, that would be awesome.
Let me write it. I used to send the message now directly. Thank you.
Yeah, I think you're asking about the exploration.
Yes.
Of oil and gas.
Yes. If we can use that kind of the machine in the river or in that of the continental zones.
Yeah,
okay, yeah.
Go ahead.
So yes, so this completion technology that I was talking about, it's not only just used onshore on the land, but also it is used offshore. So rivers, oceans, seas, we use the similar completion methodology. Some of the components might change because you have to think about all that volume of water before you hit the surface of the ocean or sea or river, wherever you are. So some of the components might change, but basic concepts remain same.
Thank you.
That's actually a good question. Okay, thank you so much, Suntum. We go to Olufemi. Olufemi, can you go ahead and activate your microphone? Try again. Oh, try again. Sorry. Try again to activate your microphone. There you go.
Can you hear me, sir? Okay, thank you very much. I appreciate Professor Hassaan Ali for excellent lecture. So my question is, what are the possible causes of a Packer failure in the well bore? What are the possible causes of Packer failure? And if there is Packer failure, what are the remedies? What are the remedies to be taken in order to safeguard the well, and prevent an uncontrolled flow of gas from the well? Can you hear me?
Yes. Thank you. Okay, so one of the common failure of the packer is we are unable to set the packer. So the packer is usually set hydraulically or mechanically, and sometimes we are unable to set the packer. That is one of the most common failure mode. The other one is if the packer is unable to seal. When the packer is unable to seal, usually that is attributed to the sealing elements of the packer. So the elastomers, that is part that are supposed to provide that sealing. Sometimes they fail as well. Multiple reasons, could be the damage during running in, could be the inability because there can be too much scale or too much corrosion of the casing that can also prevent the packer from sealing sometimes. So there are different types of failure modes, but unable to seal and unable to set are two of the most common ones for packer failure. How we actually can mitigate it is usually sometimes we have to do mechanical intervention. So you will have to send the intervention tool. Sometimes you have to cut the packer and deploy a new packer. Since packer is part of a tubing, so usually if you have to do any intervention work with the packer, you have to sometimes pull the tubing. So you have to pull the tubing all the way to the surface, do a failure investigation on your packer, and then run a new packer. That is, sometimes we have these tubing and casing patches as well that can be used to isolate the packer if you want to produce. But that's an entirely different topic. But usually packers, to do anything with to mitigate any failure with the packer, you have to pull the tubing. Okay, we can move to the next one.
CC
Yeah.
Jules, are you there?
Yeah. Okay.
ahead.
My question is, what can be the total cost? But I think the previous or the second previous guy asked for the cost olufimine. Now, my question is, how you can detect that an area contains petrol or gas and so on.
Okay. So different ways of doing it. Usually the first thing is what we call a geological survey. So the geologist will go and they will study the surface rocks. And by studying the surface rocks, they can actually deduce if there is a potential of oil and gas in that area. Certain rocks attract oil and gas. Certain rocks can actually give you an indication that there is oil and gas. Then there is what we call a seismic survey. So the seismic equipment will come. They will do a seismic survey of the area, and then they can determine if there is, because if there is a presence of oil and gas in the surface, the seismic or the sonic waves will be reflected in a very different way. And when they are reflected, when they are caught back, when they are processed, then you can determine if there is oil and gas. And then once that is done, and you have pretty good idea that there is a potential for oil and gas over here, you drill an exploratory well. So you will bring a drilling rig, you will drill a well, and you will see if it actually hits a pay zone. And then you will do a production testing, and you will try to determine how much oil is there in that reservoir. So this is the most basic workflow of determining if there is oil and gas in the area.
And, please, it's a little bit related to the Ismail questions. From the construction to the drilling, is there any AI system based to use or name to use for the completion of the task for the well drilling?
Yes. So the industry is quickly moving towards what we call autonomous drilling. So in the autonomous drilling, you don't need to have a lot of people, a lot of equipment on site. In autonomous drilling, with the help of AI, AI has not completely taken it over, but with the help of AI, certain sections of the well can be drilled autonomously. So yes, it is becoming quite common.
Okay, but I would like just the name of the system. If you mind the name, any name of oil gas drilling, how they call well bore task, well bore project, AI based system. Just a name. If you mind the name, just a name. I want to know.
Yeah, I would suggest you look for autonomous drilling on Google.
Okay.
Unfortunately, I cannot name any right now.
Okay.
Because some of that might be a proprietary.
It's okay. I can get it from Copilot or from Google search. No problem. Thank you.
Thank you.
Yeah.
Thank you, CC Jules. Hassaan Ali, are you saying that when the drilling is going down and that head has to go around rocks, artificial intelligence is able to make those decisions whether to turn to the right or turn to the left?
Yes. So some of the not the entire well, some of the sections of the well can be drilled autonomously. There is still a human sitting over there just looking at the overall drill trajectory, but the adoption to the technology is usually slower in the oil and gas industry just because it's the stakes are quite high. But slowly, certain sections can be drilled autonomously. And very quickly, the industry is moving towards drilling entire wells autonomously. We have drilled entire wells autonomously as well, but those were more like experimentation wells or wells which were not very high stake.
Yeah, that makes sense because those kinds of decisions really take like a human intuition.
Yes.